The Mach 5 packs 5,000 horsepower from a V12 smaller than a Corvette's, outperforming an Abrams tank. Today, we're reverse engineering Speed Racer's iconic car. How a 3,150-pound racer fights, dives underwater, jumps vertically, and deploys weapons at highway speeds.
You're dreaming.
That's no dream, it's a nightmare.
I thought they got rid of it.
They did, but something must have gone wrong because that's a Mach 5, all right.
The Geo V12 turbine hybrid, 5,000 horsepower from a lunchbox. The Mach 5's power plant reportedly outputs 5,000 bhp from a V12 configuration measuring roughly 180 cubic inches. For context, a top fuel dragster produces 11,000 horsepower from a 500 cubic inch supercharged V8, but only for 4 seconds before catastrophic failure. The Mach 5 sustains this output continuously while maintaining street-legal operating temperatures. If we reverse engineer the math, you're looking at 27.8 horsepower per cubic inch of displacement. Modern Formula One engines peak at 6.7 horsepower per cubic inch. The only way this works is if the V12 designation is misleading. This is likely a turbine hybrid system disguised as reciprocating pistons. Think of the Chrysler turbine car from 1963, but weaponized. The combustion chambers would need ceramic thermal barrier coatings typically reserved for jet engines, with fuel injection pressures exceeding 3,000 psi. Could it actually run? Theoretically, yes, if you're burning hydrogen or a nitromethane blend and exhausting through a regenerative heat exchanger to prevent the block from melting. The cost would exceed $4 million per engine, with rebuild intervals measured in hours, not miles. The designers basically stuffed an Apache helicopter's T700 turboshaft into a go-kart chassis. Insane? Absolutely. Impossible? Not quite.
The driver of the GRX was very lucky. Apparently he wasn't injured, but it seems as though he fainted. The doctors will check him at the hospital.
Autojacks, pneumatic launch system with 20-foot Hurricane clearance. 4 hydraulic rams beneath the chassis can launch 3,150 pounds of vehicle 20 feet straight up in under 1 second. That requires instantaneous force delivery of roughly 35,000 pounds per jack, 140,000 pounds total thrust. For reference, an F-16's afterburner produces 29,000 pounds of thrust, and it weighs 19,000 pounds empty. The hydraulic accumulators would need to be pre-charged to 5,000 psi minimum, with burst discs to prevent catastrophic line rupture. The rams themselves would be triple-stage telescoping cylinders using aircraft-grade 7075 T6 aluminum with hardened steel pistons. Deployment speed creates another problem. If you're generating 20 feet of altitude in 0.8 seconds, the pilot experiences approximately 3.2 Gs on launch and 4.5 Gs on impact. Real-world precedent? The DARPA Ground X-Vehicle program explored similar LEAP capabilities for terrain avoidance. The difference is they abandoned it after realizing the structural reinforcement required would increase vehicle weight by 40%. The Mach 5 somehow maintains a curb weight of 3,150 pounds with this system installed. It's essentially an ejection seat pointed sideways, and you can trigger it while moving at 200 miles per hour.
The first trial will begin in exactly 1 minute. Stand by.
Monocoque chassis, aluminum magnesium composite at 3,150 pounds. The Mach 5 weighs 1,429 kilograms fully loaded with driver, fuel, and auxiliary systems. A modern Mazda MX-5 Miata weighs 2,341 pounds with none of the Mach 5's hardware. This means the chassis, engine, transmission, hydraulics, weapon systems, and diving apparatus combine for barely 2,400 pounds of dry weight. The only explanation is a semi-monocoque tub constructed from aerospace-grade aluminum-lithium alloy with magnesium crossmembers. Think McLaren F1 construction circa 1992, but a decade earlier and exponentially cheaper. The fiber-reinforced polymer body panels would need to be load-bearing, functioning as stressed skin components rather than cosmetic fairings. But here's the problem. Aluminum-magnesium alloys are notoriously brittle under repeated high-G impacts. The autojack system alone would create stress fractures within 50 deployment cycles unless you're using friction stir welding at every joint, a technique that didn't exist commercially until the 1990s. The Mach Five's chassis would require complete teardown and inspection every 500 miles of hard use. They built a Formula One car that thinks it's an armored personnel carrier. The maintenance budget would exceed the purchase price annually.
Please let it win speed! 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 Speed!
Rotary cutter blades. Carbide saws at 8,000 RPM. Twin rotary saw blades deploy from the front air intake, mechanically driven by the primary drive shaft. To effectively cut through timber roadblocks or enemy vehicle chassis at speed, these blades need to spin at minimum 8,000 RPM, with cutting edges measuring 18 inches in diameter. That's 377 feet per second of blade tip velocity, faster than most rifle bullets. The blades themselves would be laser-honed tungsten carbide, the same material used in industrial sawmills and armor-piercing ammunition. But mounting them to a driveshaft-powered system creates catastrophic gyroscopic forces. At 8,000 RPM, each blade generates approximately 450 pound-feet of precession torque, trying to yaw the vehicle off-axis. Real-world analog? The M728 Combat Engineer vehicle mounts a 165mm demolition gun and a hydraulic dozer blade, but it weighs 56 tons and moves at 30 miles per hour maximum. The Mach 5 attempts this at 250 miles per hour, with a power-to-weight ratio 40 times higher. Every time Speed Racer hits C, he's gambling that the frame welds hold and the front axle doesn't snap. It's a weapon system designed by someone who's never heard of Newton's third law. Belt tire system, adaptive traction for all-terrain dominance. Control B deploys retractable belt tires, essentially tank treads disguised as tire chains, to distribute the 5,000 horsepower output across unstable surfaces. Standard racing slicks would vaporize instantly under that torque load. The belt system increases contact patch area by roughly 300%, allowing full throttle operation on gravel, mud, ice, or sand. The engineering challenge is the transformation mechanism itself. You're replacing pneumatic tire contact with a segmented steel-reinforced belt in under 3 seconds, while the vehicle is moving. This requires the tire tread to retract into the wheel well while spring-loaded belt segments extend outward, driven by individual electric motors at each hub. The power draw is substantial. Each belt motor needs roughly 50 kilowatts, 67 horsepower, just to maintain tension and prevent slippage, meaning 268 horsepower of your total output vanishes into the traction system alone. Modern all-wheel drive systems lose about 15% to drivetrain friction. The Mach 5 loses 5.4% just keeping the belts engaged. Lockheed Martin's MRAP all-terrain vehicle program explored similar adaptive traction concepts and concluded it was mechanically feasible, but economically absurd for anything short of Mars rover applications. The Mach 5 does it with 1960s hydraulic.
This is Trixie in the Mach 5 calling Inspector Detector. Speed and I have found out the Mammoth car is not just a racer.
Underwater propulsion, 80-knot submersible operations. The Mach 5 can seal its cockpit, deploy a snorkel intake, and operate submerged at speeds up to 80 knots, 92 miles per hour. For reference, the fastest submarine ever built, the Soviet K-222, maxed out at 44 knots, displaced 10,000 tons, and required a nuclear reactor. The Mach 5 does this with a V-12 and an oxygen tank. The physics here are brutal. Drag increases exponentially underwater. Moving at 80 knots requires roughly 16 times the thrust needed at 10 knots. You'd need approximately 3,200 horsepower just to overcome hydrodynamic resistance, leaving 1,800 horsepower for actual propulsion. The exhaust system would need to be reconfigured as a pulsed jet nozzle, expelling combustion gases through vectored thrust ports. Structural integrity becomes the limiting factor. At 80 knots underwater, dynamic pressure on the forward surface exceeds 14,000 pounds per square foot. The polymer canopy would need to be 3-inch thick polycarbonate laminate rated for 500 psi, essentially the viewport from a deep-sea submersible grafted onto a race car. The designers basically said, what if we made a Formula One car fight a torpedo, and somehow made it work? On paper, anyway.
Calling the Mach 5, come in, Speed. Trixie calling the Mach 5.
I'm in the middle of a race, Trixie. Don't talk to me now. Can't you wait till it's over?
Homing robot Gizmo, tactical recon drone circa 1967. Control G deploys an autonomous aerial surveillance drone from beneath the hood, a concept the US military wouldn't operationalize until the RQ-1 Predator in 1995. Gizmo transmits encrypted video feeds, carries messages, and performs forward reconnaissance using what appears to be a miniaturized turbofan engine and gyroscopic stabilization. The technical hurdles are staggering. A functional drone in the 1960s would need vacuum tube-based radio control, analog video transmission, and mechanical autopilot systems, none of which existed in packages smaller than a suitcase. The power requirements alone would demand a dedicated battery pack weighing 15+ pounds for a 20-minute flight time. Modern analogs like the Switchblade 300 loitering munition weigh 5.5 pounds and carry advanced digital optics, but they benefit from lithium-ion batteries, solid-state electronics, and GPS navigation. Gizmo predates all of this by a decade and somehow fits inside a compact sports car. Speed Racer had a Predator drone before the Air Force knew they needed one. They just didn't know what they had.
Oh, I hope Sparky's been able to reach speed with the new brakes.
Deflector shield deployment. Transparent armor in 2.5 seconds. Control-D deploys a transparent polycarbonate canopy over the open cockpit, converting the Mach 5 from a roadster to a sealed interceptor. The canopy must be bulletproof, aerodynamically neutral, and deployable in under 3 seconds, all while maintaining optical clarity for high-speed navigation. Polycarbonate's tensile strength is roughly 9,000 psi, far superior to standard automotive glass, but still insufficient against armor-piercing rounds. You'd need a minimum 1.5-inch laminate construction, similar to bank teller windows or presidential limousine glazing. At that thickness, the canopy weighs approximately 90 pounds and requires electric actuators delivering 400 pounds of lift force. The real problem is aerodynamics. Deploying a canopy at 200 miles per hour creates instantaneous drag equivalent to opening a parachute. The Mach 5 would decelerate at approximately 1.2 Gs unless the canopy profile is pre-optimized for the vehicle's existing airflow patterns. Modern fighter jets solve this with hydraulic actuators and pre-computed deployment sequences. The Mach 5 does it with a button on the steering wheel. Either Pops Racer is a savant aerodynamicist, or Speed only deploys it below 80 miles per hour.
Doesn't matter to me what his reasons are for wanting to win. I wouldn't be playing fair if I let him win the race on purpose.
But Speed!
I'll see you when the race is over, Trixie.
Auxiliary fuel system. Oxygen injection for underwater combustion. To operate submerged, the Mach 5 switches from atmospheric air intake to an onboard oxygen supply, effectively running the engine on a closed-loop combustion cycle. This is identical to how World War II German submarines used snorkel systems, except the Mach 5 does it while moving at 80 knots instead of 8. The oxygen tank would need to supply roughly 12 cubic feet per minute at full throttle. That's 720 cubic feet per hour, or approximately 6 industrial K-bottles worth of compressed O2. At 2,200 psi storage pressure, you're looking at 300 pounds of gas storage alone. But here's where it gets interesting. Pure oxygen combustion burns 40% hotter than standard air-fuel mix. The exhaust gas temperature would exceed 3,500 degrees Fahrenheit, hot enough to soften the aluminum block and warp the cylinder heads within minutes. You'd need to inject coolant directly into the combustion chamber just to prevent the engine from self-destructing. NASA uses similar closed-cycle combustion for rocket engines. They also rebuild those engines after every test fire. The Mach 5 treats this as a casual feature you toggle between traffic lights.
Speed doesn't answer. Come in, Speed. It's not like Speed to disappear like this.
Manufacturing cost analysis. The $40 million go-kart. Let's total the bill. Custom turbine hybrid engine, $4 million. Aerospace-grade monocoque chassis, $2 million. Hydraulic launch system, $6 million. Submersible conversion kit, $8 million. Rotary weapon systems, $1.5 million. Adaptive belt tire mechanism, $3 million. Tactical recon drone, $2 million. Integration and testing, $14 million. Grand total, $40.5 million per unit, assuming you're building 10 vehicles to amortize R&D costs. For context, an F-35 Lightning II costs $80 million and has ejection seats. The Mach 5 costs half as much and can't fly, but it can cut through trees and jump over landmines. Maintenance is where it gets obscene. Those hydraulic accumulators need inspection every 20 cycles. The turbine engine requires teardown every 50 hours. The belt tire system has 147 moving parts per wheel. You'd need a dedicated pit crew of 12 technicians and a mobile workshop semi-truck. Annual operating costs would exceed $8 million. Pop's racer either has a CIA black budget, or he's the greatest scrounger in automotive history. So there it is. The Mach 5 would bankrupt a small nation, require technology that wouldn't exist for 30 years, and demand a maintenance schedule that makes F1 teams look casual. But those 1967 designers actually nailed the core concept: modular auxiliary systems controlled via a centralized haptic interface. Modern military vehicles are only now adopting the function button paradigm Speed Racer normalized. The autojacks are fantasy, but DARPA's Ground X vehicle program explored the same concept in 2016. The underwater propulsion is impossible with combustion engines, but electric submersibles are making it feasible. Gizmo the drone? We call them switchblades now. Which system impressed you most? The 5,000 horsepower turbine hybrid or the pneumatic launch system? Either way, the Mach 5 was decades ahead of its time. Until then, this is Control G, signing off. Keep your belt tires engaged.